absolutely interrupt anytime to ask questions if points are left unclear. I rather have questions as we go along than all at the end. It would be much more fluid and lively. So thank you, Chris. It's a really wonderful opportunity to be here to discuss our work with you guys on Zoom. In fact, yesterday I was preparing slides and I told my wife and kids that I was going to give a talk in Roma, and my wife was like, "What? You're going to Roma? You didn't tell me about it." Well, it's much easier on Zoom, but I'm looking forward to really physically visit the labs in Rome at some point in the future. Anyway, so today I will share the floor with Thibaut Roch next to me. So you will have two people talking instead of one. And the reason is that Thibaut is just finished, defended his PhD thesis. He will stay at EPFL for a few more months or around the EPFL. And he will tell you about his latest results and in particular what's behind this good-looking image here on the left. And I think it's nice for Thibaut to talk because he was one of those PhD students going through COVID, and it was harder to get chances to go to conferences and travel. So that will give you a nice forum also to showcase your work. This is work, in fact, that started some time ago, and I want to acknowledge also Fabien Barras, who was a student just before Thibaut in my team at EPFL. He's now at Oslo University with François Renard, and I really want to acknowledge this long collaborations we've had with Eran Bourbinder at Weissmine and his collaborators. This is really collective work about richness and complexity of sleep events at a frictional interface. All right, so this is my disclaimer slide. I realize today that I am talking in front of my a community which is generally not my community. I've never been to a seismology conference, and I don't know many of the names that are present on Zoom today. So I want to say that I do realize that you are dealing with amazing complexity. Complexity that is, let's say, geometric with false complexity at different scales. And I'm taking here a picture showing that there's not a nice plan for the faults for sliding into a curve. It's really complex at different scales. And you're also dealing with diversity of mechanisms. So I have a list, that could be ongoing on the right. And on top of things are buried. Things are on the ground with lots of, let's say, uncertainties. So if you are thirsty today of discussing the mechanisms that you have on the right or this type of complexity across scales, well, I'm sorry, this talk will not quench your thirst, okay? So my apologies. In passing, I also want to say that complexity exists in general in tribology. So this is a very popular image taken from a fairly recent review paper led by Antonis Vakis that shows a typical, let's say, engineering interface on which you have friction. And you have a lot of different mechanisms. So complexity is there also in what you could call simple engineering problems, but nothing is simple when you talk about tribology. And this has led to this another beautiful, I find, review paper from Meng and Ludema. That's my favorite papers of all time. That gives you a list of 300 different equations for friction and wear with lots of fit parameters. Some of those equations have up to 25 different material constants going in there. So it's really complicated. And we also put this type of complexity aside. And today, that's the overview of the talk. We will deal with extreme simplicity. And the ingredients are very simple. And I want to acknowledge one of the students from my lab who helped me make this beautiful animation. Pay attention. There you go. We have sliding of a 2D elastic body on top of another two-dimensional elastic body. Okay, so extremely simple. The bodies, in fact, we will play with the height. So sometimes we will have a finite height, let's call it h, but it will be equal height on both sides. Sometimes we will take to be semi-infinite, they will go to infinity, so that we don't have to worry about interactions with the boundaries on top and bottom. but they are elastic bodies, pure elastic. At the interface, we will have right-hand state friction. This is something you know a lot about. We will play with the boundary conditions. At times, I have this arrow here, but it's a bit more complicated than this. At times, we will impose traction boundary conditions, and at other times, we'll impose displacements of velocity boundary conditions. And we'll see how things change. And on the side of this box, we will have periodic boundary conditions, so that we make some sort of infinite body sliding on top of each other. And the properties will be homogeneous. No heterogeneities, will be the same Young's modulus on both sides, same Poisson ratio, same friction parameters all along the interface. And elastodynamics. And yet you will see richness and complexity will emerge out of this extremely simple system. Okay, this will be a talk in which we will use numerical modeling, numerical simulation. So I just want to say a few quick comments on this. In my lab at EPFL, we develop a lot of tools. It's a bit of bread and butter. That's how we try to look at physics problems that are, go from the nanoscale all the way to very large scales. And we have a track record of developing open source software. So in principle, all what we show today, you can download the software. They're on GitLab. You can install them at home and regenerate the results we will show. They also run on HPC platforms, so they are scalable algorithms. And today we'll use two codes. We will use Archon2. So Archon2 is a generic finite element software that can do statics and dynamics. We can do contact detection. We can model damage with different techniques, cohesive zone modeling. We can use also non-local continuum damage models such as phase field model for fracture. It's fairly costly, the method, because we need a mesh, and we will mesh the bodies entirely. So you have to pay a price for this. But with this method, you have a very good control of the boundary conditions. You can deal with finite size systems. The second type of software we'll use is Cracklet, the second logo here. And Cracklet is a spectral boundary element code. It's much faster than our FE software Archon2, because we only put nodes at the interface, and then we'll have kernels to include the interactions with elastic bodies above, but then we deal with semi-infinite elastic bodies on top and bottom, right? We do not have finite boundaries. Okay, so we have both softwares that we will use for this talk. I want to say also that Thibaut will share the talk with me, is in a line of PhD thesis that took place in my lab at EPFL on a general topic of fractional rupture. We started looking at this during the thesis of Dave Kammer. Now Dave is a prof at ETH Zurich. He also developed a very meaningful along the years with Jay Feinberg. Then Fabien Barras followed the footsteps of Dave. Now he's a postdoc at University of Oslo, working with François Renard. Thibaut is just finishing. Following Thibaut, we have Roxane now in the lab that's coming to me with a very interesting background in geophysics. And I'm really counting on a dialogue with your committee, in fact, to develop meaningful collaborations. Okay, so this is the outline of the talk. I will deal with the first bullet, and Thibaut will take over. So what I will talk about is this notion of dynamic stress drops. And we'll tell you what this means. And I will tell you, and I'm already saying the conclusion already there in the outline slide. We'll come back later, but I want to repeat several times to make this clear. When we will have a stress drop, this will help us explain why friction can be looked at, understood with the tools of fracture mechanics. So this is as politically correct as I can put it. I think Jay and Adja will agree with this. But when we will have no dynamic stress drops, then friction is friction. And I lose this friction is fracture. Okay? So we try to understand this. I will pass the floor then, the virtual floor, to Thibaut, who will tell you something that makes a lot of sense. Boundary conditions matter. Am I applying displacement on the boundaries? Am I applying stresses? It will matter, and this will help him segregate between different types of mechanisms at the interface, from being pulse-like to being crack-like. And then he will go back to this figure that I showed on my first slide, this nice figure, discussing the emergence of statistical complexity in very, very simple system with no, and I put the no in bold here, with no heterogeneities. All right, so I'm starting the first part, lab earthquakes. And you are very much aware of the very diverse body of work you can find in literature, and this is only a small fraction of the groups working on this. You have an image taken from Jay about lab earthquake experiments, but monitor very, very carefully so that you have access to the strand fields close to the interface. You have access also to details of what is sliding and not, and you can measure velocities of fractional fronts. You can interpret stresses in light of LEFM. And I've also taken an image from a thesis of Federica Paglialunga and from the group of my colleague at IPFL Marie-Violet, which is a very exciting experiment of also lab earthquakes, but on analog material, but at a very large scale. Here you see 1 meter. That's tell you the size of the setup, which will allow my colleagues here, collaborators, to look at stress heterogeneity. So we have a wealth of data that has been generated and keep being generated, trying to understand lab earthquakes in light of LEFM. But what crack-like properties emerge from the system is not clear, and I will go back to this. So I need one slide to refresh a bit of memory on fracture mechanics. And this analogy to fracture mechanics for frictional system, which is in fact not so obvious, right? So if you talk about a crack, that's on the left-hand side of the slide, things are quite clear. We have a crack. This crack is disturbing the line forces. On the crack list, you carry no stress. So sigma yy is equal to 0. Therefore, you need to concentrate the line forces at the crack tip. And this results in what is known as a stress intensity factor. And the stress intensity factor, you can compute with it an energy release rate. And we all know about Griffith's energy balance. G is equal to GC, which controls really the crack growth and the dynamics of crack. So it's quite clear that on the left, we have a crack, and that, of course, fracture mechanics applied for a fracture problem. Fracture is fracture. Now, on the right, we have now here a frictional interface. So one question you could ask yourself is, well, do we have creation of new surfaces? Because we already have an interface upon which things slide, and we do not get new cracks, new free surfaces that have been created. Maybe at the level of microcontact, but it's not so obvious. Also, what's not so obvious is that we have this frictional interface carries stress. It carries a shear stress that eventually, if you reach a steady state sliding, has to equilibrate the far field driving stress tau d. If the top body moves at a constant velocity on top of the second bottom body, that means the sum of the forces has to be equal to 0, and tau d, my driving stress, has to be fully equilibrated by stresses at the interface. And if it's fully equilibrated, then you have no reduction of the stresses, and therefore you have no stress singularity, and therefore no energy balance will not apply. So those are things that are on the back of my head. A second bit of difference between fracture mechanics and friction is that when you deal with frictional system, you can have a healing. And when you have healing, you can develop interesting modes of sliding, including slip pulses here, where you have a zone that is sticking in front of a pulse, but behind the pulse, and this is why you have a pulse, you stick again, the velocity is 0. And this is not something you will observe for mode 1 fracture. All right. So let's use the numerical tools and look at this problem with a simple 2D system. So the ingredients I recall for elastodynamics is to consider 2D, either plane strain in mode 3 or plane stress in mode 2, linear elastic, finite or infinite bodies. That will be velocity or stress control. We'll start with stress control. We'll introduce a perturbation at the interface to nucleaton event. So initially it's at rest. It's sliding from what I will show at essentially zero velocity, scraping, we're going to perturb the interface. And this paper tells you about the method we use for this. And we'll generate what we call a rupture front that is going to be, in between brackets, violent, rapid. We have right and state friction at the interface, and there will be a dialogue, an interplay between bulk and interface properties. So at the interface, we have right and state friction. So I don't have to, I can go fairly quickly over the slides because this is very well known to your community. But I want to remind you that there is progressive healing of the interface. Upon hold time, you will have a logarithmic increase with time of a static friction coefficient. And then if you, and this is related to the growth of the microcontacts with time. And then upon a change of a sliding velocity, you will have a very rapid transient effect, and then gradually you will reach a new steady state value of a dynamic friction coefficient. And this can be captured. Again, this is due to microcontacts, and it's fairly complex what happens at the scale of a microcontact, but we can capture this with phenomenological rate and state friction laws. So playing with the parameters, you can fit the experimental data, and depending on the choice of A and B, you can have velocity weakening behavior or velocity strengthening behavior of the interface. And I throwing one data here from a paper from Barcina et al. That shows that velocity weakening, strengthening is also observed, is generated to a lot of frictional interfaces. You see here the steady state value of a dynamic friction coefficient as a function of V, the sliding velocity. And you see there's a region for which it's velocity weakening, and then it strengthens again. Okay? So in the talk, we'll consider both velocity weakening laws and velocity weakening, then strengthening at a critical velocity. All right, so let's look at this very simple 2D system with rate and state friction law at the interface, with boundary conditions that are, in this first part, load control. So we have applying a vertical stress, sigma. We are compressing the system. And then we have the driving stress, a shear stress TODI, that is going to be there to help us store energy in the system that will release, will perturb the interface, and we're going to generate what we call a frictional rupture front. And we are now portraying this very, very macroscopically to start on this steady state value of a friction coefficient as a function of the sliding velocity. So in a lab, maybe with a rotary shear apparatus, you could measure at different velocities and control the value of a dynamic friction coefficient, and you will report data from an interface law that will follow either this brownish curve, the velocity weakening and then strengthening, or this orange curve that is velocity weakening. And what we control in a system is the boundary conditions. We control TODI, the driving stress. And TODI is portrayed here by this horizontal green line. And you can put it up or down, okay? If you put it up, you have more energy in your system. You can lower this bar. And I want you to realize that this bar is intersecting my brownish curve at 3 different points. Those are the yellow stars. The first intersection point is an equilibrium point in the creep region of my friction law. And I will have then steady sliding because my frictional stress at the interface is exactly equilibrating my far field driving stress. I have a second intersection point on a velocity weakening branch. That's an unstable point. And a third intersection point is on a strengthening branch where, again, we have a stable system where the stress at the interface exactly equilibrating the far field stress. Okay, so this is my most important slide. And please interrupt me if you have questions on this one. The critical slide. And it's both extremely simple point that I want to make, but also I find extremely difficult to understand and to explain. So hopefully I will be successful with this. We're going to talk about dynamic stress drop. So we're talking about a fast rupture problem. And the details are in this paper here on top. So we are applying this vertical line. That's my boundary condition, so stress that I apply far field. We're going to generate an event, a rupture event. And what we can show is that the stress, steady state stress, shear stress at the interface is not equal to the far field stress study, but it differs by this quantity in red, which is the radiation dumping term. Because when we load the system, we generate an event, we'll have a noise, we'll have energy taken away from the interface. This energy is a radiation dumping term. It's really function, notice, of the material properties, and you are aware of this radiation dumping term. We all know this in the seismology community. But it's function of the bulk properties, the shear modulus mu, the shear wave speed CS, and it's proportional to the jump in velocity at the interface from the initial maybe creep velocity V0, which was 0, and now we are jumping to a finite velocity Vs. This is energy taken away. This radiation dumping term gives you a stress drop delta tau. And in the presence of a stress drop delta tau, then you have this notion that friction is fracture, or maybe better, friction can be explained in the light of the tools, with the tools of fracture mechanics. So the game we're doing.
Jean-François, yes. You said we can interrupt, right?
Yes, absolutely.
So can you remind us briefly, this temporary steady state, is it behind the rupture front? Is there a rupture front here, or is that somehow the entire interface is in this state because of what the initial conditions are?
So let me show you the shear stress, how it looks at a snapshot in time. That's the shear stress tau as a function of position X along the interface. The far field stress is tau d. Here, everything is normalized by the normal stress sigma, but here you have the value in front. The front propagates left and right. So we have two fronts here. There's one on the left and one on the right. But in front, ahead of the tip, we have the far field stress tau d. Then you have the singularity that you develop. And behind the front, you get this residual stress tau res. Okay? So here we have what we've called a temporary steady state. A temporary steady state along part of the interface, but it's growing with time because the two tips propagate at a velocity here, which is close to CR. So it's not CR, it's a rupture. Velocity of the CR means velocity of the rupture front. Okay?
Understood, yes, thanks.
Understood. So this is a radiation dumping term that gives you a stress drop. So now go back to your friction law that you are measuring in a lab with rocks, with a rotary shear apparatus. You get maybe this brownish curve, velocity weakening, strengthening, or maybe you get this pure velocity weakening branch. This temporary steady state is given by the sum of this interface law and this radiation dumping term. So you're adding tau SS, you're adding to it the radiation dumping term, which is function of a velocity. You see this Vres. Well, Vres is this velocity on this axis. So let me add up this linear dependence on Vres to my friction law, and I get this dashed line. Okay, you can do this on MATLAB or Mathematica. You add to your data, experimental data, you're adding this radiation dumping term, and you get a dashed line. And your steady state friction and velocity at the interface is given by the intersection of the green line with this green horizontal line with this dashed line. To get this point of intersection. This is giving you the stress drop and incidentally also the velocity, the sliding velocity at the interface. So you get, that's what I write here, an effective steady state friction curve that gives rise to temporary stable sliding, because of course this radiation dumping term will travel through your system, eventually bounce back from boundaries and go back to the interface. Okay, at which point the velocity will change again and you will lose the stress drop progressively. I will go back to this. So does it work?
Francois,
You can take,
sorry.
yes.
Can I ask you, but why during the most of the weakening stage, you assume that the friction is at the steady state? Because in this case, your stress drop is not associated to the weakening. Am I confused?
We have a tempo, you see on this curve, we get something that's fairly flat here. So we have a steady state. I can show data also for the pure weakening law, for which we also get a temporary steady state. You get some sort of a plateau. I mean, you can discuss, how quickly you establish this plateau. If it's very, very flat, you could discuss that to within a few percent. But you do get a temporary steady state.
Massimo,
That's before you get reflections from boundaries.
I think the steady state is there, Massimo, because this is rate and state friction, right? So it's logarithmic in dynamic slip rates, and then the dynamic resistance is roughly constant. If there were like shear heating or something like that, then it wouldn't be that steady.
Okay, you're talking about heating, about melting and things like this.
Well, something, right? Yeah. If there was shear heating and friction properties would be evolving because of that, then it may not have been, it may not be that flat.
Yeah, but okay. I understand this is correct, that this is because you are sliding more or less at the constant velocity. But again, the stress drop, it is should be associated to the amount of decrease associated to the weakening, not only to the radiation damping approximation.
So that's a point. So it's function both of the friction law, because if you have a brownish curve, the details of the experiments matter. It's a function of friction, and it's function of bulk properties, the stress drop that you develop. It's function of shear modulus, shear wave speed. So it's both interface and bulk. There's this interplay which makes it very, I find, very subtle.
And what about?
I'm a little confused with just I think it's just notation. That so your delta tau comes from your radiation damping term, and so that's not meant to imply static stress drop, right? It's not, or is it meant? It's meant to imply a dynamic stress drop.
This is why Nadia told me on Friday, and I followed her lead. She told me call it dynamic stress drop. See, I have it in the title, and I've even added as a subcaption for fast rupture. We're talking about fast events, and you hear noise. If you do an experiment, you hear a crack, a boom. Things are moving, right? You can hear it.
Mm-hmm.
All right.
Okay, so there is no static stress drop anywhere in this problem right now.
Now it's a dynamic stress drop. We're doing with dynamic event with a dynamically getting rupture front.
All right, we're communicating. Thank you.
Emily, you're right. And because, the static stress drop will establish itself when the crack will arrest or rupture will arrest, right? And it may be very different. And
Yeah, okay, got it.
In my case, it will not arrest because I'm maintaining 2D. My driving stress is maintained constant. And eventually, I will show you, it reaches steady state sliding, where friction is friction, not fracture anymore. Friction is friction, but always moving, but more or less the constant velocity. Newtons, law,
In the next
force is equal 0.
In the next slide, Jean-François, you don't, maybe it's not clear, but you don't seem to have any kind of a breakdown zone or cohesive zone. That's partially what Massimo was asking too, I think. So
I'm developing a non-zero stress at the interface because of friction.
no, but there is a cohesive zone, right, Jean-François? It's just very sharp here. The cohesive zone is from the peak down to this residual.
I will have a slide on this where we we'll try to quantify what is a process zone, what is what you call a cohesive zone, damage zone.
perfect.
All right, so does it work? Does it work, this prediction? So we took data from Nadia, Ares, and Vito from Caltech, where they have access in their experiments to both independent measurement of both the sliding velocity, Vires, and a stress drop, delta 2. And I recall that both those are related by this term, the radiation dumping term. So the data points are shown in green and red. The prediction is this continuous line. We can also, with our code, with the spectral code cracklet, we can also generate a range of events for which we change 2D, we change our driving stress, and we measure delta 2 from we get rupture events that look like this, and we can measure the drop of stress from ahead to behind the front. And what we predict is a continuous line in this plot, and the data, numerical data, as a point. So it works reasonably well. Now, again, this is a finite time effect. This friction is fracture effect is a finite time. So this is a hard plot to comment, but I think we need to spend time on this also. So those now are finite element calculations. With finite element calculations, we can deal with finite systems. So my block has a height of h. And the waves nucleated at the interface, when we have this sudden event, will propagate in my elastic domain, will reflect on the top and bottom and come back to the interface. And we're going to follow, I'm going to play this movie twice. First, we look at what we have on the left, and we are looking at the slip velocity in meters per second along the interface. We are along the interface. And initially, when we play this, if I succeed to play this, how do I play this? Maybe I should stop the marker. There we go. Saccadé. They're not working properly here.
Not really.
I apologize. I think the sharing is not working right. Very strange. Is it going smoothly for you, the movie, on your side or not?
No.
No.
No. Okay. Well, my apologies. My point, what I wanted to say is that the slip velocity, initially along the interface, you have a singularity velocity because you have a stress drop. But then you are losing the singularity, gets the slip profile of a material point velocity is more or less homogeneous. And each time the waves come back, each time the wave is coming back to the interface, the velocity is increasing a little bit till you reach a steady state value of more or less homogeneous sliding along the interface. And that's what I call friction is friction. And on the right-hand side, there's the second plot where we follow 2 points along the interface, a red point and a blue point. And you see that those 2 points are inching their way. They are crawling with their teeth and nails back to this third intersection point with my horizontal line, which is TODI, and my friction law. And it's only when I reach this point that I have, a true steady state. My far-field stress is fully equilibrated with my stress at my interface. And this is due coming after multiple wave reflections. Okay, so it's two-phase. Friction is fracture if you have sudden rupture and a dynamic stress drop. And then later time, it's really a frictional problem. And this was a question that I had. If you have a stress drop, then you can use energy balance. You can use G is equal to GC. So let me skip this because I see Thibaut is getting nervous and I'm using all your time. But we can compute the energy release rate, taking either the stress profile along the interface, the stress field, or the velocity field. So we can have an estimation from the numerical results of the dynamic energy release rate, G. We can estimate also what is being dissipated along the interface. And this is what we publish in this paper. I give you the reference here if you're interested to look at the details. But we can estimate what is a process zone by going back to definition of the parameters of my right-hand state friction law and go back to definition of what is phi state variable, which is thought as the average lifetime of the macro contacts. The evolution law is phi dot is 1 minus v phi over t. So if this v phi over t is larger than 1, then you have a decrease of the average contact area. So we can find the points along my interface which satisfy this criteria of v phi over d larger than 1. And this gives us a pink region here, this colored pink region. And we only use the points in this colored pink regions to compute the frictional dissipation. So if we take only this to estimate GC, we find that G over GC, G was evaluated on this slide with the stress field, GC is evaluated with the pink region. We find that G over GC is very close to 1 throughout the history of my rupture front position along the interface. So very close to 1. Yes.
Jean-François, sorry again. Can you explain how do you identify the point in which the breakdown energy and the fracture energy becomes breakdown energy? So what controls this transition?
So we say in this paper, we said the fracture energy is going to be given by the points that follow in this pink region. The points in the pink region. So on this axis, we are plotting, you see V phi over D. And it's a red curve. See this red curve, it goes up and then goes back down. And we only take the points that satisfy V phi over D larger than 1. That gives us a point in this pink region. For those points, we say GC is 1 over the velocity VC times the integral for the along dx, along the interface, for the points that satisfy V phi over D larger than 1 of my shear stress minus my residual stress.
Okay, I understand, but I think that, okay, we have to be careful because there is, we have in the community some terminology issue about breakdown energy, but that is another topic. Sorry for that.
I do know this, and I'm not trying to resolve this issue here. I'm just saying for this paper, what we have done, with this scheme, we compute GC, then we have a very close match between G and GC, G over GC is very close to 1. And if you look at the traction as a function of slip for 1 point along the interface, okay, you see that the traction goes through some complicated bumps, ups and downs, right? But what we say for us here is fracture energy is this red part here of this curve. And the blue part, the remaining work will be the remaining of this breakdown work. And this breakdown work, see, is increasing with slip in blue curve here, but my fracture energy here is constant.
Jean-François,
okay.
How do you define T sub r, tau sub r?
Yes, so tau sub r is my
residual, right?
Is my residual stress, which we take at the end of this process zone. But you know, there's also a long tail, a progressive breakdown. So basically, how you define this, you're going to change a bit what you call fracture energy and breakdown energy.
Because you know, I see you're not going. You know, you're not when you define that the rupture doesn't yet know what the tau sub r will be, right?
No,
you know, because you're taking the part of the process which hasn't reached tau sub r yet.
Yes, but we have a value of tau that we can get from this green curve that we take within this part where we have this breakage. I think the key point is breakage of the microcontacts here. That we say this is a process zone. We are breaking microcontacts. We decrease the real contact area at the microcontacts, and this is what we call our fracture energy. But so this is a bit of a longer story. In fact, I wanted to add a slide on this, which I did not, with Eran, Bourbider, and Effin added a paper following this on what they call the non-conventional singularity, where in fact the tail has some influence of the exponential, the progressive weakening behind my tip will have an influence also of the type of singularity you develop. Okay, let me move to conclude this first part of the talk, because I had pretty much all the time, and Thibaut has 20 minutes for 2 more parts. This concludes the first part, and I know it's not maybe resolving the debate about fracture energy versus breakdown energy fully for the committee, but for me, it's very clear that if you have a dynamic stress drop, Then this is a condition for what I call crack-like behavior. It's a finite time effect. I really want to insist on this. Once you have a dialogue with the boundaries, then and wave reflection, then this is gone, the stress drop progressively will diminish, and then we'll transition to when there's no stress drop, when friction, that with the point that friction is friction. Okay. For the second part, Thibault is going to play with the boundary conditions to develop a bit further the richness we can develop on this frictional interface.
Okay, so thanks, Jean-François, for this first part. So everything that Jean-François presented was dealing with applied stress far from the interface. And we wanted to know what would happen if we choose the other, let's say, kind of boundary condition, which is applying displacement or velocity. And in order to understand the fundamental difference between stress-driven frictional rupture and velocity-driven, I'm just going to repeat a few things that Jean-François described before. So if we consider that we have this generic rate and state friction law with some strengthening and weakening branch, and that we are applying some stresses, we again have the far-field stress here in yellow, and we have several intersections that Jean-François described before. So there's two different stable points, one that corresponds to some sticky condition with almost zero velocity, which is stable. And we have this long-term steady state after the reflection and after all the transient effects have disappeared. And Jean-François also mentioned that we have another intersection point, which is on the rate weakening branch of this friction law. And this point is fundamentally unstable, meaning that if the system is sufficiently large, it cannot homogeneously slide at this velocity because it is subjected to the development of some elasto-frictional instabilities. So if you want to force the system at this velocity, it will accelerate and nucleate some rupture. So this is for stress-driven frictional rupture. And now we wanted to ask, what if we are imposing the velocity instead of the stress? So now we have some velocity imposed on top and bottom. So again, it's always symmetric. The system is really simple. We are using elasticity and homogeneous bulk and frictional properties. And we choose the velocity to intersect our friction law in this velocity weakening branch here. And so we have only a single intersection with our constitutive behavior, but this point is by definition unstable. So we wanted to ask, to wonder what kind of dynamics can emerge in this system. And as it cannot accommodate this velocity, it means that some part of the interface has to slide at a larger velocity, while other part of the interface has to stick. So basically, if we force the system at this velocity, V0, we are expecting the emergence of a steady train of pulses that is schematized on the bottom here. And basically, this solution is expected to be stable. So the propagation velocity of this train and the shape of this train are expected to be stable. So let's see what happened in reality. So we conducted numerical simulation for different cases. So we considered finite and infinite bodies, but I'm just going to show you an example with the infinite case. So we are using the spectral boundary integral method that Jean-François briefly introduced at the beginning of the talk. And there's one really important thing to remember here is that in order to impose velocity-driven condition on this specific body, it is not possible to apply the velocity far from the interface because we are only discretizing the interface, and everything that happened in the bulk is considered through some kernels, and there's no communication with the far field boundaries. So in order to try to mimic this kind of velocity boundary condition, we decided to impose what we call an average velocity condition at the interface, with the assumption that the interface is always at steady state, that the average velocity is always equal to the imposed velocity V naught. So this will be important for the following developments. On the top left, I'm going to show you a video, and I hope it will be better than the previous one. You will see the velocity field at the interface evolving with time. And originally, we are starting from some small homogeneous velocity V naught. We add some perturbation, and as this velocity is in the rate weakening branch, it will develop some rupture. And let's see what happens. So you should start to see some oscillation. You have the development of several frictional rupture forms that are propagating. And I just want to remind you that we are always dealing with periodicity on the side. So the pulses or the object that we are seeing are interacting with each other several times. And if we wait long enough, we have a single object that remains in the system. And this is a sleep pulse, as we were expecting before. And I just want to show you the same kind of results on a different visualization. So here you have a space time plot of the velocity field, exactly what you saw in the movie. And you can see the original coarsening of the interface with several different rupture objects propagating and interacting all together. And if you wait long enough, you only keep a single pulse in the system. And this last object is stable, its propagation velocity is constant, and its shape as well. And this is a generic result, meaning that if we change the height of the system, so if we do finite element simulation with small heights or let's say intermediate height, we always get to this result of the emergence of a single pulse in the periodic system. So basically, this validates the expectation from velocity-driven system. And we took advantages of this to study the properties of this single pulse. So I'm not going to get into too much details, but I want to take one specific example of the properties we were interested in. And this is the propagation velocity of the sleep pulse. So before, when Jean-François was talking about stress drops, we were looking at some objects that were crack-like. But now we have sleep pulses that are fundamentally different from the original representation of a crack in fracture mechanics. But if we look at the details of the fields near the rupture tip of the frictional pulse, sleep pulse, we can see that we have, again, some singular stress and velocity fields, and also some notion of stress drop. So on this plot, the tip is, let me put the pointer back. The tip is here. This is the peak of the pulse. In brown, you have the velocity field, and in yellow, you have the stress field. And you see that we have some reduction in stress inside the pulse. And if you look closely at the shape of the fields near the tip, here you have like a double logarithmic plot of the velocity. We find back the -1/2 slope characteristic of fracture mechanics. So it means that even if we have an object that is fundamentally different from a crack-like rupture, it seems to have the same properties as classical cracks. So we wondered if we can use tools from fracture mechanics to describe the behavior of this sleep pulse. So we assumed that the concept of local energy balance is satisfied here. As Jean-François showed, it was satisfied for crack-like rupture. But here, we don't know. And using this energy balance, we derived an equation for the propagation velocity of the pulse. So some kind of pulse equation of motion. And I'm not going to give you the entire equation, but basically the propagation of the pulse is function of the input in the system, the bulk parameters, and also the frictional parameters. We need some estimates of the fracture toughness. And as Jean-François shown before, we can estimate it based on the fields, if we assume energy balance, or we can compute it, assuming that we compute this estimation of the process zone, or we also have some semi-analytical estimate. And well, what we saw is that this pulse equation of motion that is only based on tools from fracture mechanics gives really good results. So on the left here, you have the measured pulse propagation velocity, and here you have the prediction. So I'm not going to get into more details, but in this paper, we have a comprehensive pictures of all the other characteristics of the slip pulse, the width and the periodicity. And well, we are using basically fracture mechanics to describe their properties. So I'm going to jump.
Thibault, one quick question, please.
Yes.
So in the simulation you showed maybe 2 slides back, there were different heights of that peak of this velocity, this normalized velocity, and
yes,
those correlate with what? How do we produce bigger or smaller pulse heights?
So at the end, when we kind of describe all the equation, it depends on the driving velocity. So V naught and the size of the system. Because if we increase the system size, we can always host a single pulse in this system, so it will affect the shape of the pulse. And the velocity, basically the velocity and the size of the system have an impact because they change how many LC, so how many critical length scale in terms of frictional instabilities we can have in the system. So by change, which is, yeah.
Okay, thank you.
Okay, so for this really small part, we are now dealing with velocity-driven system, and we have a fundamentally different structure mode that emerge, but that can still be described and understood using tools of fracture mechanics. But I want to remind you that for this small part, we assume that we had a constant average velocity imposed at the interface with this constant, let's say, mimicking velocity-driven sliding for infinite systems. So now the question we want to ask is what happened if we don't have this imposed velocity at the interface and we let the system evolve freely? And this brings us to the topic of emergence of statistical complexity in frictional system. And usually in physics, when you have complexity, it can have 2 different origins, which is either complexity emerged from complexity in the properties or the bulk properties of the frictional properties themselves, or it is due to the strong nonlinearity of the mechanism at play. And in most of the literature, people are putting heterogeneities in their system in order to observe this complexity. And we were wondering, can we observe complexity in the systems we are using until now, which are completely homogeneous in terms of bulk and frictional properties? So we are conducting finite element numerical simulation of this setup on the left. It's the same you saw until before, but just represented in a different way. And now we are using a friction law that is purely velocity weakening, but the results are qualitatively the same if we use the velocity weakening strengthening law that we had before. So what happens when we do velocity-driven experiment like that? So we put a little bit of noise at the beginning just to nucleate a rupture. And you see on the bottom left here, a typical response in a space-time diagram, again, of the sliding velocity. And compared to the plot I showed you before, it's much more chaotic. We don't have a single rupture event that is stable, but we have some patches that slip, then the entire interface stick, and a lot of complexity emerge. And on the right, you have the picture that Jean-François used in the first slide, which is the same kind of results, but slightly different representation, where you have the space, the cumulative slip, and the color indicates how much time a point that the interface took to slip a given distance. So basically, it gives you some information on the slip velocity. And we are using this map to identify independent frictional rupture events and to build statistics on these events. And what we see is that we have broadly distributed event characteristics. So here I'm showing the average slip, the duration, and the seismic moment. So several orders of magnitude, but with some distinctive change in behavior between small events and large events. And we basically understood that by looking into details at the dynamics of the events themselves. On one side, we have, let's say, what we call a large propagating event that would be pulse-like or crack-like rupture that we are usually talking about in this context. So these are the large events. And on the left, the small events, they are non-propagating. It's some slip that is accumulated at the interface and is mostly triggered by waves that are reflected in the elastic bulk. So some patches that slips, but this patch is not growing. And in order to distinguish between these two typology of events, we used some really simple criterion that is based on the average slip of one event. And we compare this to the characteristic size of the microcontacts from the rate and state friction law that we are using, which is D. And we say, okay, if the slip is lower than D, it means that we don't have a propagating rupture. If it's larger, it's a propagating rupture. And if we separate the statistics for this from these two type of events, we find that small events are characterized by power law scaling, while the large one have another statistical distribution, which is log normal. And you can see this in green and the log normal fit in yellow. And so the question is, why do we have this complexity? Because I remind you, we do not have any type of heterogeneities in the system. So I'm just going to go directly to the end of this slide. And I'm going to try to explain what happens here. The statistical complexity arises because we have dynamical complexity. We have intricate sequences of events in time and space. So, and these complex series of events create some self-generated heterogeneities at the interface, not in the frictional properties themselves, but in the state field and the stress field. So here you have an extract of this space-time diagram with a zoom on some events, and you can see in bright colors that we have some really big slip here, then it stops. This big event is represented here for the state and the stress field. You have in black what was before the event, and in green what is after the event. So for the state, you see that we are breaking microcontact, so you reduce the state variable in some part of the interface, while the rest is aging. So we are developing some heterogeneities. And for the stress fields, well, we have some rupture that is propagating. So when it arrests, it will let some stress concentration at the end of the rupture. All is building some heterogeneities at the interface. And based on these really heterogeneous conditions, this will decide where other events are triggered and are arrested. So if you look into details, you can witness some really small events that are triggered in the location of some stress concentration. So just another point in this study is that we are dealing with finite age, and this finite age is important because we have reflections and stress waves in the body. This is what is likely triggering the small events, but this has also some impact on the dynamics of large events as well. So we went back to a really simple case where we had a single perturbation. So a single event is nucleated. You can see it here in the middle. And what we observed is that the duration, the lifetime of these sleep events basically corresponds to the time of reflection of the waves from the interface to the top of the body and back, which means that the reflection of waves is a mechanism to stop rupture. And so we expect that if we double the size of the system, we will have, well, twice as long event. That's what you see on the right. And in fact, in this case, it's not stopping altogether the rupture, but it's changing what was a crack-like rupture into 2 sleep pulses. So the interaction with the boundaries have a strong effect on the dynamical complexity. And it has also an effect on the statistical complexity in the system. And this timescale, 2h over the shear wave speed, basically gives you the change in behavior in the probability density function. So here you have some example with varying h for both the duration of an event and the average sleep. And I just want to conclude on this slide that we were looking at a system that is extremely simple with 2 blocks that are homogeneous, everything is elastic, but still we are observing some kind of complexity in the sense of a broadly distributed law. And this is reminiscent of, well, the actual laws that we are observing in geophysics, which you are all aware of, like Gutenberg-Richter or Omuri's law. And even if we have a system that is really not as complex as a reality, we can already get some complexity just by a complex frictional behavior that is a rate and set friction and interaction with finite boundaries. And well, I think we are way overdue in time. I don't know. So I just want to thank you all for listening to us. And I hope you have some more questions for Jean-François and I.
Not too long at all. Perfect timing. I'll invite people to unmute and join me in thanking for a fabulous talk. Really interesting.
Thank you.
So please use the reaction button at the bottom of your screen to raise your hand, because then it'll put us in some order and it'll be easy to decide who's going to ask a question after Nadia Lapouche asks the first one. But I especially want to right now, and I will do it again, to invite early career people to join the conversation. Raise your hand and ask a question. Nadia.
Thank you for the wonderful talk. So, you know, it explains so many things. I like both parts. I, in fact, prefer that there were 2 seminars. But, you know, of course, it's good to get a bit of review on both. So I have lots of questions, but I'll just ask one for now. And then, you know, if people can stay, I can ask more. So, you know, this complexity, you know, you mentioned some, you know, it's a fascinating study of the second one. And you mentioned 2 sources of complexity that people use. There is a third source, which is numerical instability. And so I'm looking, you know, at these simulations, and they have very strong weakening. So this is kind of like flash heating extended back, you know, several orders of magnitude and slip rate. You have events 4 orders of magnitude in terms of seismic moment. And we cannot get that in the well-resolved boundary integral calculations without, you know, simulating for weeks. So I was going to ask, what's the numerical resolution, and have you checked that the results do not depend on it? Like, for example, do you have events that are just 1 cell size in your finite elements? And if so, then, you know, there is a complexity at the small scale just due to numerics. And there's been a long debate about that in the 90s. So I'm just wondering about that.
Okay, so thanks for the question. So first, your point about strong weakening. These results are not limited to just purely weakening friction law. We also did them with some strengthening branch, and we observe the same qualitative results. It just takes much longer in terms of simulation to observe as many events to build some meaningful statistics. And in terms of the resolution, so we worked on the time step and well, the spatial resolution of the system, because it's already really difficult to do finite element modeling with rate and state friction. And we made sure that it's not apparently dependent on this. And when we are identifying our events, to make sure that we are not, well, the way we are identifying our events, we can talk about this during a long time, but the really small events are kind of excluded from the statistics, because for us, it's just like the way we are treating our data.
I understand, but there are well-defined ways, right, of measuring resolution. One is you have a frictional, right, and state friction law. So there is a notion of nucleation size. And also there is this cohesive zone size that Massimo was asking about. And for the numerical results to not depend on these, both need to be resolved with, several cell sizes. And so even though you don't count the small events, if they arise, they still give rise to complexity and stress, which is, grid dependent and not necessarily physical process dependent, right? So that doesn't mean that the simulation is not valuable, right? It just shows that, if indeed there is numerical resolution of this kind, it's just that you have really strong complexity on small scale, which very well may be present in fault zones and so on, right? It's just, if it's present, I wouldn't characterize this as a very uniform interface. I would actually characterize this as a very non-uniform interface at the smallest scale. And there have been papers about that in the early 90s that I can, send you. There was, but so you're saying there are small events, one cell size, and you just exclude them.
So the small events, I think, are related to how we treat the data, but the process zone and the nucleation size are well below the discretization. Like we need a lot of elements.
Well above.
Well above.
The mesh is much finer.
The mesh is much finer, but it's difficult to say, because LC, depending on the velocity at which you are sliding at the interface, it's not. I'm not sure how it's defined for this kind of system, because it's not. We are not starting from just V that is homogeneous and stress that is homogeneous. So maybe we are resolving it for the initial condition, because that's, let's say, a reference simulation, but it's possible that for really specific condition, it might be different.
But I think that's a notion we should rediscuss further, Nadia, when we plan our Zoom meeting soon, including Thibaut and also Roxanne. Sure. The only thing we can do is, and when we've done this, is with our finite element calculation, is refine the mesh, reduce the time step, and as I told you on Friday, we reduce the time step by a lot, by a factor 100, to make sure that the results are stable. Yes. And that's what we've done, right? And the results we present are at least converge in some statistical way.
Yes.
But it would be interesting to discuss, because the results are fascinating. I'm just wondering what's the proper interpretation of the origin. But yeah, thank you so much.
Massimo.
Okay, thank you. Thank you very much for the presentation. It was really illuminating. So I have two questions. One question is the following: am I wrong that if you apply your equation to a singular degree of freedom spring slider, after the steady state, your velocity would stay on the limit cycle? Because this is what we get with right state. So that means that when you end the breakdown, the stress drop, and you reach the steady state, the velocity do not increase. Simply stay at the steady states and decrease with nearly constant or decreasing friction. In your case, your velocity continues to increase after reaching the steady state. Now, the question is, if this is due to the fact that you have not a single degree of freedom, but you have a line or a 2D system, and therefore, if this is the case, you need to be sure that this dynamic interaction are causing this behavior. So it is fully dynamic. Am I wrong in interpreting your result?
It's fully dynamic. You are perfectly correct. With a single degree of freedom, I don't see how you would be able to capture the dynamics in the system. So you will be missing this. So it wouldn't work, right? So for us to have this continuous jump in velocities at the interface let's talk about the average velocity, because velocity is not a constant throughout the interface. We have events occurring, right? But the average velocity, let's say under stress control system, my average velocity will go up a little bit by a little bit. That's a movie I wanted to play earlier, but that did not work, unfortunately. But the average velocity will go up by bits and bits and bits till we reach a true steady state, where my velocity is very close to be constant throughout the interface in a system we've looked at, and precisely at the point where my friction law is exactly equilibrating my far field stress. So Newton's law, sum of the forces equals 0. I have 2D on top pushing to the right, but I have also the same balancing stress at the interface pushing to the left. That it's fully created. Sum of the forces equals 0. Therefore, my body is moving, let's say, as a rigid body with a constant uniform velocity within some noise. Okay? And this is why you are crawling your way to this equilibrium point each time you have wave reflection. And this you cannot get with a single degree of freedom. You need to model the bulk elastodynamics for this.
Yeah, I understand. But we did many years ago 2D in-plane simulation with right state friction. And after nucleation with this 2D, actually the velocity would remain at the limit cycle, would not diverge.
What do you call a limit cycle?
I mean, the limit cycle of the dynamic system. Of the limit cycle of the dynamic system.
Yeah, I'm just gonna say stick slip, right, Massimo?
Yeah, exactly.
It would not be steady at the end. Many systems converge to stick slip.
Okay.
Yeah.
But are you pulling on your system with another spring?
Sorry?
Are you pulling with your 2D system with another spring to get the stick slip?
No.
So what is your boundary condition?
Okay, I don't remember because this was nearly 20 years ago. I will send. I have to read again the paper, and I will send to you.
But I'll be happy to discuss this with you. Maybe you organize another Zoom to discuss this paper. It's possible that if your system height is much further away, that the bulk elasticity will give you the stick slip. Basically,
Okay, and my second, okay, I am more than available. My second question concerns the interpretation of the sleep modes. Because if I understood well your simulation, you are generating a sleep of different amplitudes. Okay, so you do not distinguish the different elements in the spectrum of sleep behavior. So you do not distinguish slow sleep or other fast sleep. So you have a different amount of sleep that you transfer into magnitude. Because of sleep modes for many seismologists or geophysicists means that you have low frequency events, you have slow events, other type of sleep mode that are not only dynamics, they belong. So just to be sure, so your sleep events, they only differ in the amount of sleep and therefore on the sort of magnitude. That's it.
So the width, the speed at which they travel, the height, this can be characterized, and it's function of the applied velocity that you maintain and of the system size, right? So so what you say is correct, Massimo.
No, but if I can interject just for a sec, I think from what Jean-François showed me on Friday, they are different modes, Massimo, as well, because some of them are slow. You know, some of them are fast, but some of them are much slower. So in that sense, they could be
but I would
modes.
not call them slow in a sense you understand them slow. It's
because it's still a few % of the limiting
of the elastic speed.
Yes.
So they still for all purposes, you know, reasonably fast. We have variations, we have degrees of how fast they are or how, but I wouldn't those are not slow earthquakes or slow sleep pulses that we think that with creep, with other type of mechanisms. So they're propagating still reasonably fast, I would say.
Thanks.